calculate the period is to measure the distance, maybe this distance, from, let's see, from here to here. Okay? That's the period of the wave, which is about, let's say this is 251 milliseconds, and this one is about 270, maybe 280 milliseconds. 250 to 280, that's 30 milliseconds, right? And 30 milliseconds, so that's the period. What's the frequency? How do you get the frequency from the period? Just go 1 over the period, right? So what's 1 over 0.03? 100 over 3, it's about 33 hertz. So the frequency of this wave right here is about 33 hertz. Now if we go up, let's go up to this arrival right here. I can't quite, let's see, probably show it. So this arrival is about 33 hertz, somewhere in that range. What about this arrival right here? Into there. How much is this distance right here? Maybe even this one right here. Goes from 100 milliseconds down to about 145. Right? So that's 45 milliseconds, which is about 50%. It's a period that's 50% more than this one. Right? So the frequency, so basically if the period is 45 milliseconds, then we do 1 over 0.045, and we're going to get about what for the frequency? A little bit more than 20 hertz, right? Maybe 21, 22 hertz. So this wave is propagating at 21 to 22 hertz. This wave is propagating at 30 plus hertz. Which wave comes in first? Which one has which one comes in first, and which one has a higher velocity? The move out of this arrival right here is about what? It goes from 100 milliseconds at 20 meters. You can't quite see it, but it's probably about 135 or 140 milliseconds at 44 meters. So 24 meters divided by, let's say, 40 milliseconds is what? So 24 divided by 0.04. 2400 divided by 4, it's about 600 meters per second, right? So this wave is traveling at 600 meters per second. This wave is traveling at a velocity of about, let's say, 22 meters to 44 meters over and it's 50 milliseconds. So 22 meters divided by 0.05. 2200 divided by 5, which is going to be about 400 meters per second. So what we've just done by eye so we have this picture right here. I'm going to, a lot of times what we want to do again is we want to draw a stick picture of this. So let's just like this, and then there's a part like this. And the frequency of this is about, what did we say, 22 hertz, 21 hertz. And the velocity was about what? 600 meters per second. The frequency down here is about 33 hertz. And the velocity is about 400 meters per second. So let's plot that on a frequency velocity chart. take a look. I don't know if this will work or not, but let's take a look at an intermediate point here. You know, I'm not even going to bother doing that. I'll probably be wrong. We've got 2 points. I was lucky with that. And we could draw a straight line, or let's just draw a curve for one. Okay, let's say that there are some other points that we didn't measure out here that kind of look like this. So what do we obtain out of this? And notice all we have to do is look at the records to do this. Right? I haven't done anything other than shown you the record and pick some frequencies out and measure the velocities associated with those frequencies. I haven't done any magic mathematics or anything. So what I've generated out of this is B versus F, velocity versus frequency. And we know that velocity versus frequency, velocity is going to change with frequency for a Rayleigh wave if we have a medium where the velocity, shear wave velocity changes with that. So what we've done here is we have measured the Rayleigh wave dispersion curve. Actually, we measured it for the fundamental mode of the Rayleigh wave. So this is essentially what we're going to use, this dispersion curve. We're going to build a velocity model of the Earth. And we're going to see if we can simulate the Rayleigh waves that match our dispersion curve. So we're actually going to take the Earth model, a layered model of the Earth, and we're going to, using simulations, model the dispersion curve that we would get from that particular Earth model, and iterate until we match the measured dispersion curve. And then we have our shear wave velocity curve. Now, how could we do more with this data right here? So this is, right here, this whole package is really one wave. This whole thing, from here all the way up to there, is the Rayleigh wave. And the reason that it's so spread out and gets more spread out with time, if you look up here, the Rayleigh wave only extends from about 75 milliseconds to 150 milliseconds. It's 75 milliseconds of total duration. If you go out here, we're looking at 125 to over 300. Okay, so the Rayleigh wave is spreading out in time. Well, that makes sense because of dispersion, right? There are components of that wave that are traveling with a velocity of 400 meters per second, and there are components of that wave that are traveling with a velocity of 600 meters. So this dispersive wave disperses in time. It spreads out in time as we go from the shorter offsets to the longer offsets. Does that make sense to everybody? Okay. There are other arrivals on here. You see what I would call a first arrival. Anybody see the first arrival on here? That little speck up here, right up there. So if we really wanted to pick that arrival, we have to blow this thing up and zoom into that area. This display is not the greatest for picking that arrival, but you can kind of see that the arrival doesn't, and there's no deflection here, and you finally get some deflection there. So let's look at this latest part. Now, let's just look from here to here. The travel time looks like it's increasing about, I don't know, 5 milliseconds or so in the distance of 10 meters. Okay, so we go 10 over 0.05, or 0.08 distance